All right. Today we're going to talk about polar coordinates. Are rectangular or Cartesian coordinates. Now it's Cartesian coordinates because it was developed by Rene Descartes, the philosopher, the I think, therefore I am guy, cogito ergo sum, yeah, mind body dualism, yeah. He came up with the way of graphing with our rectangular coordinates with the x's and y's when trying to work with analytic geometry. So trying to show relationships in geometry in a visual way with a graph. Polar coordinates are a different way of showing points or plotting points. Instead of having your x and your y, you're going to have an r and a theta. So rather than going left and right to get to a point up there, the polar coordinates are going to go on a direct path. That distance is going to be r, and the angle you turn is going to be theta. So we want to turn in a certain direction and then walk or move a specific distance to get to the point. Now, the alternative is that if you want to do your X's and your Y's, that is perfectly legitimate. But we want to have our other ways of representing because sometimes polar is going to be a little bit easier to deal with. Sometimes rectangular is a little bit easier to deal with. So we want to be able to convert back and forth between the two. Now, I said we rotate, then go out. You could also go out a certain distance and then rotate up. So whichever way you want to do it, it's fine, but we have to do both. Zero is not going to be called the origin. It's called the pole. So kind of like your North Pole type thing. The positive x-axis is called your polar axis. And now how do we make our conversion between the two? So I'm going to redraw this triangle that I just had up here. There's our x. There's our r. There's theta. Now, of course, this is a right angle, so we have a right triangle here. And the key to converting between our polar and rectangular coordinates is trigonometry. Now, since x and y are the legs of this triangle and r is the hypotenuse, we know that r squared is going to be the square root of x squared plus y squared. There, Pythagorean theorem. A squared plus b squared is c squared, x squared plus y squared is r squared. Now we want to get our r by itself, so we will square root this. But we're only going to focus on the positive r for the most part. Now, r can be negative. We'll address that a little later on. But for the most part, we want our r to be a positive number. So here's one equation that we're going to look at. Now with our tangent, or excuse me, with our theta, y is the opposite, x is the adjacent. So tangent of theta is y over x. Now you can arctangent, but you need to be careful that if your arctangent only gives you angles in the first and fourth quadrants. So if you have a situation where you're going to be up here in the second quadrant or down in the third quadrant, this will not work. So I like to call that an a theta sub r. It's a reference angle. It'll help you to find your theta, but it's not your theta itself. So either one of those are going to be good. Other things are, so r sine of theta gives you y. Over r. So r cosine of theta gives me x. Now over here, this is good, or those two equations are going to be useful, or three equations, depending on how you think of it. You know equations. These two down here are going to be good when you're going from polar into rectangular coordinates, because we know our r's and thetas and we're looking for our x's and y's. So having those angles is going to be extremely useful, or having those equations will be useful for our conversions. Now, another thing, in our rectangular coordinates, there's one way to show a point. It has a certain x, it has a certain y. In our polar coordinates, there can be multiple ways to represent a specific point. So say we wanted to do this. We're going to go out 5 units and rotate, say, pi over 4 radians. And we want to go to there. So 45 degrees. We could have this point just be written as 5 coordinates. We'll put a little p there to designate it. But there are other ways to do it. So we always write it as our r and then our theta. And we typically want our theta to be radians. But otherwise, we could do it. Rather than just going straight there, we could go the other way. So this could also be 5 and then negative 7 pi over 4. We could also go around to the pi over 4. Or we could go around again and add a 4 pi, or again and add a 6 pi. So a general rule is that r, and then we would have our theta plus so we're going to add a multiple of 2 pi, where n is going to be an integer. Now for this one right here, we went, instead of just thinking of it as going the negative direction, you could consider as going up to what we did, n would be a -1. So regardless of how you think of it, that equation governs our similar points, or other ways to writing our point. But then there is another way of doing this too. Copy here. If I want to go there, we could still do r5 pi over 4. That's still going to work. And I said that we normally want our r to be positive, but it doesn't have to be. A negative r would mean we're going in the opposite direction. So we could go and turn and look the other direction and then go a -5 units. So basically you're walking backwards. So -5, and then here would be a -4. Or we could rotate that way. So it would be a -5, 5 pi over 4. Regardless, if you want to use a negative r, subtract an odd number of pi's. So 2n gives me an even number, so we'll do 2n plus 1 pi, where n is an integer. So a couple different ways we can think of it. And do some of these conversions. And since we started this, let's change our 5 pi over 4 from polar into rectangular. So knowing your trig here is going to be extremely important. So we know r and theta. So let's use our equations. Y is r sine of theta. And square root of 2 over 2. So therefore, 5 square root of 2 over 2. Our x is 5 cosine of theta. So it's 5, and then also square root of 2 over 2. So it's going to be the same value. And if we're going at a 45-degree angle, we're going up as we are going, as much as we're going out. So we should get the same numbers. So it's going to be 5 square root of 2 over 2 and 5 square root of 2 over 2. Next up, let's go the other way. Let's say we have the point of 1, -1, and that's rectangular. Let's write that in our polar coordinates. So now our r is the square root of x squared plus y squared. So square root of 2. And then tangent of theta is our y over our x. So it's -1. So where's tangent equal to -1? It's either in the second quadrant or the fourth quadrant, because that's where it's negative. And then filling in our sides, we know it's an isosceles triangle. It's also a right triangle. So we know that our reference angles are going to be 45 degrees. Now we want 1, -1. So we want the one down here in this fourth quadrant. So our theta could either be a -pi over 4 or a 7 pi over 4. Or add or subtract 2 pi n to either of those. So in polar, square root of 2, and we'll go 7 pi over 4. Why not? So you notice that our numbers work out nicely and giving us nice points in rectangular and nice points in polar are not always going to happen. So we have to be careful with that. So watch with your conversions, your like square roots or fractions with these conversions. Next up, how do we draw these graphs? Or how do we convert our equations? So before we even get into the graphs, let's look at equations. We can actually convert the equations as well. So what's going to happen if we say r equals 2? Square root of an x squared plus y squared. And that is an equation that's written in rectangular coordinates now, so we're good. But if you want to know a little bit more, square both sides. And this is the equation of a circle. And if you think about what's happening with r equals 2, it tells us that our radius is 2. It does not tell us what our theta is, so we have to account for every theta. So you want to go 2 units out in every direction. And we get a circle. Let's try another one. Let's say they tell us that theta equals pi over 3. So for here, we need to change this into our x's and y's. So let's take the tangent of each side. Now, tangent over 3 is just square root of 3. And then we know the tangent of theta, y equals square. And if you think about graphing this, it's just a linear equation with a slope of square root of 3. So we're going up square root of 3 over 1. So square root of 3 is about 1.7-ish. So our slope's going like that. Yeah. Now these graphs do get a lot more complicated or a little more involved. There's a bunch of different ones you can do. So I have a, you can take a look at that one. But let's get into some of the calculus of this. So with these polar graphs, we want to be able to come up with tangents of them. How can I line to a curve? So figure out our dy dx. But we can think of this in terms of differentials, and we can do a dy d theta divided by a dx d theta. Now, how is that going to make this work? So let's go take a step back. Remember that our y is r sine of theta, and our x is r cosine of theta. Now, typically, whenever we write our polar coordinates, we make r a function of theta. So let's replace that r with a function of theta. We typically want r by itself if it's just r's and thetas, so we can rewrite it this way. Now that we have of theta, we can then take those derivatives. And now I'm going to not use the f of theta. I'm going to go back and just use the r just to make that stand out, just make life a little easier. So if we're going to take the derivative of this or this, it's going to be a product rule. So our first, there's going to be a derivative first, the first times derivative of the second, divided by derivative of the first times the second plus the second times derivative of the first. Now, derivative of cosine is negative sign, so let's just combine that together. So right here is the formula for your derivative. But it's overall not too bad with its individual components. Now, if we want a horizontal tangent, we're looking for where our numerator is 0. Vertical tangents, where is the denominator? 0. As long as the other one's not 0. So let's take a look at an example of this. Have r equals 1 plus sine of theta. And if you haven't already watched the video, this is what's going to be called a cardioid. The other one about graphing. Cardioid. And the graph's going to look something along these lines. And so you can see where it gets named cardioid because it kind of looks like a heart. This one's an upside down heart. And we want to find the slope of the tangent line of the tangent at theta equals pi over 3. So let's use our equation that our dy dx is going to be derivative of r, which is going to be cosine, times sine, plus r times derivative of which is cosine. On the bottom, derivative of cosine times cosine minus r times sine. So let's do some distribution and combining. On top, we have a cosine sine. When we do the distribution, we have another cosine sine. So we have 2 cosine sine plus cosine. On the bottom, we're going to get a cosine squared. Then minus sine squared minus sine. All right, doesn't help us too much. Now, if we're in terms of simplification, there are some things we can do with our double angle formulas that we're going to see right there and right there. But we can also do a little bit of manipulation. Plus too much, but it's something we can do. Is on top, we could also factor out a cosine. And then on the bottom, our cosine squared is 1 minus sine squared. So we get a -2 sine squared of theta minus sine of theta plus 1, which we could factor that into 1 plus sine 1 minus. So a couple different things you could do. Take of how you want to do your simplification. But there's our derivative. So we have that equation. From here, we want to evaluate where theta is pi over 3. So let's make all of our thetas pi over 3. And since we have this equation here, let's go ahead and use it. Cosine of pi over 3 is 1/2. 2 times sine of pi over 3, which is square root of 3 over 2, plus 1. On the bottom, 1 plus square root of 3 over 2 times 1 minus 2 square root of 3 over 2. Let's do some simplification. So we have that 1/2 there, and then this is square root of 3 plus 1. And then down here, we're going to FOIL this, but for the time being, 1 minus square root of 3. Now, a neat little of getting rid of fractions is multiply the top and bottom by whatever the denominator of this little fraction is. And now it's multiplication on top, so we can only multiply those two together and they'll cancel. And then I can distribute this one only to one of these. So we end up with square root of 3 plus 1 over 2 plus square root of 3, 1 minus square root of 3. If we pull this bottom, we're going to get 2 minus 2 square root of 3 plus square root of 3 minus 3. Which means we're going to get a -1 minus square root of 3 factor that out, negative square root of 3 plus 1. Those are the same, so our slope is exactly -1 there. Now, if we want to find out where we have vertical and horizontal tangents, so let's write our equation down again. This is where having it in the factored form will come in handy. And if we want where it's horizontal, we look at the top. So let's set this whole numerator equal to 0. Now, since it is factored, we have to just set each thing equal to 0. Cosine equal to 0. And where's 1 plus 2 sine equal to 0? For this, we're going to limit our responses only to between 0 and 2 pi, just for simplicity's sake. So here is our theta would equal 0. And let's go from 0 to 2 pi, not inclusive. Then we can look at the bottom one. So where is sine equal to a negative 1/2? Our theta there is going to be 7 pi over 6 and 11 pi over 6. All right, so that's our horizontal. Let's look at our vertical. We'll come back to this later on. Points where this happened. So we have to find our, we can do it here. Let's find our R's. So remembering that our R is 1 plus sine of theta. And we found our thetas. So sine of theta is 0. So 1, 0 will be one of our spots. Then when we plug in 7 pi over 6 and 11 pi over 6, our sine is a negative 1/2. So 1/2, 7 pi over 6, and 1/2, 11 pi over 6. Potentially. We'll come back to these points in a minute. Let's look at our vertical. So looking at our bottom, 1 plus sine, and then 1 minus 2 sine. We want to set that equal to 0. So once again, each of our individual spots. So where is sine equal to a negative 1? And where is sine equal to a 1/2? This theta is 3 pi over 2. And actually, I made a mistake up here. Cosine is 0, not at 0, but at pi over 2 and 3 pi over 2. So that one's out. And this would be at 2. At 0, 3 pi over 2. But we'll address that one in a second. And then down here would be theta is pi over 6 and 5 pi over 6. So our points would be 0, 3 pi over 2, 3/2 pi over 6, and 3/2 5 pi over 6. So again, plugging these thetas into our R equation. Now notice that on our list, both of them had this one. So we don't want that as either of our answers. We get 0/0. Something weird's happening. But now if we look at our graph that we drew before, setups are happening there and there and up there. That makes sense. Our verticals are happening here and here. That makes sense. But the one that we crossed out, the 0, 3 pi over 2, that's our cusp. So something weird happening there. It's not differentiable. Therefore, a 0/0. All right, that makes sense why we have a situation that we don't want to, that we cannot handle. But remembering your basic equation for the derivative, knowing how to do your conversions between polar and rectangular, knowing your common trig angles. And if you haven't already, watch the other video on just graphing, so you have an idea of what these graphs look like. So whenever you're doing the evaluation, it can make a little bit more sense and you can visualize it a bit.